guys, this is going to be the final chapter, which is going to be the radiation chapter, guys. Alright, so look at the first question here. What do they want from you? It says that an electron moves into a uniform magnetic field. The arrow shows the initial direction of the motion of the electron. The direction of the magnetic field is into the plane of the page, guys. So if I'm given this kind of situation here, I have to understand that I am given the magnetic field and I am given the direction of this electron. The first thing that you need to do to tackle this question here is to understand that we always associate alpha particles like current. We always associate alpha particles like current, and we also associate beta particles like the electrons here. And because the electrons and current always flows in the opposite direction, you have to understand that if an electron is flowing towards the right, the so-called current right is going to flow here. And if you identify that you are essentially supposed to use a left hand basically point your index finger, which is your magnetic field, in towards right, and open up your current finger, point it towards the left. Basically going to point down, indicating that it will be reflected towards the page and the trajectory will look something like this. Okay, so this is what you are supposed to do. For the second question here, it says that the scattering of an alpha particle by a thin metal foil supports the nuclear model of atoms. Why are alpha particles used in this theory? When they talk about this thin metal foil here, they are basically referring to the gold foil experiment, right? The reason why we use alpha particles is because the alpha particles are supposed to bombard the nucleus, right? And this is because whether it has a lot of empty spaces or all the masses are concentrated in the center. It's always good to draw out the whole decay process. If it goes through alpha decay first things first is going to spit out a helium particle for 2 lah. From here it would have become 214, 82 and some random element lah, let's call it X first. This X element will yet again go through another beta decay, which is 214 and 82, right? And once it goes through a beta decay, it's going to spit out electron 0, -1, which will make it into a different element, 214, but it will be 83 here, right? So from here, they ask about the nucleon number, right, which is obviously 214 lah, right? Then the proton number is 83, and that's why your answer is going to be C for this question here, guys. All right, then moving on to the next part. The scientist carries out the experiment using a sealed source which emits beta particles. The range of beta particles in air is somewhere around 30 cm. Which precaution is most effective to protect the scientist from the radiation itself? Handling the source with long tongs? Definitely, you're not supposed to touch it with your hands. Keeping the temperature of the source low? This has no effect. Opening all windows? This is not a gas chamber. Washing his hands before leaving the laboratory? It's not going to protect him out, but it's definitely good hygiene, right? So A is definitely the answer here. Which rule describes the nature of alpha particles and beta particles? Alpha particles are definitely helium nuclei, right? So it's either A or B. And, it's not beta, it's gamma rays. Gamma rays are definitely in the electromagnetic spectrum. For those who are confused, please revisit the electromagnetic wave chapter. Right? Then moving on to this next part here. An iodine isotope 131I decays by beta emission to an isotope of xenon. state the number of each type of particle in a neutral atom of 1 3 blah blah blah. Right, so they want me to find the proton now, which is obviously going to be 53 lor. The neutron is always the nucleon number minus the proton number, which is 131 minus 53 here. It's essentially going to be 78 lah. Right, and the electron numbers are definitely the same as the proton numbers because they are neutrally charged, guys. Only ions will have more electrons or more protons. Now, of course, state the symbol in nuclide notation for the xenon nucleus is going to be Xe. It's going to be, 53 here at the bottom. Oh no, it's going through the... Sorry, it's going through... It went through the beta decay already, guys. So from here, it's going to be like 13153. Go through beta decay, which is 0, -1, and going to be 13154 here. Alright, so it's going to be Xe, 131 and 54. This is supposed to be your answer. Okay. Then the final question here. The background count rate of radioactivity in the laboratory is 30 counts per minute. This is the background radiation. A radioactive sample has a half-life of 50 minutes. 50 minutes is the time taken for it to decay by half its current amount. The sample is placed at a fixed distance from the detector. The detector measures an initial count rate from the sample, including background of 310. So without the background, it starts off with 280 lah. Right. On figure 10.1, plot a suitable point and draw a graph of count rate from the sample corrected to background. Right, so initially it's at 280 ma. So if it's 280, this will be 290, 280 will be somewhere around here lah. Right, this is your 280 mark. Then after 280, 50 minutes later, which is going to be somewhere around here, right, it will be half its current amount, which is 140. 140. If this is 100, here will be 110, 120, 130, and 140 here. This will be the amount. Then after that, another 15 minutes goes by, it will be 70. Another 50 minutes go by, it will be 35. So another 50 minutes, it will be somewhere around 100 lah, which is going to be 70. So if here is the 100, here will be 90, 80 and 70. You'll get somewhere around here, and the final one, which is 150, is going to be somewhere around 35. Right, so if it's 150, it will be somewhere around here. Here will be 10, 20, 30 and 35. So essentially you're going to get a curving graph that looks something like this. Of course, you can draw it nicer with your pen and pencil, right, and ruler if you need it. But it's supposed to curve, guys. It's supposed to be like a curving line that goes downwards. Please draw it nicely in your own time. Okay? And moving on to the next part here. The diagram shows a current carrying wire. The wire is at 90 degrees to the magnetic field. The direction of the magnetic field is yet again into the page here. If you have current and you have magnetic field, obviously you're supposed to find the force, right? The force must be your Fleming's left-hand rule. I noticed that the camera is going to be inverted, but this is the left hand, the one on your left, guys. So you're getting clenched into a fist, point the magnetic field into the screen, right? Your current this time will be towards the right, and this time opening your thumb here, you'll get the thing that goes upwards lah, right? So it's definitely going to go towards the top of the page here, guys, right? Then the radioactive substance emits radiation at a rate of 600 emissions per second. 4 hours later, it emits a radiation of 300. So this is essentially your half-life, because 600 to 300, right? What is the half-life of a substance and what's the rate after another further 4 hours? The half-life is definitely going to be 4. After that, it's going to be 150. It's not going to be like 600, 300, 0. It doesn't work that way. It's half its current amount. Half its current amount is this, half its current amount is this, guys. So it's 600 to 300 to 150. Alright. Then, moving on to the next part here. The nuclide notation for an isotope of silver is blah blah blah. How many nucleons are there in a nucleus of this isotope? Nucleon is basically proton plus neutron, which is on top of the nucleon number, so it's none other than C, right? The equation represents an isotope of radium decaying to an isotope of radon with the emission particles of X. What is particle X here? So looking at this is missing 4, this is missing 2. It can be no other than the helium particle 42, right? Which indicates that it's an alpha decay. An atomic nucleus decays by one or more radioactive decay process. What causes the proton number to decrease by 1? If I want the proton number to decrease by 1, let's go for an example model. Here will be 50 and here will be 25. If I go with an alpha decay followed by a beta decay, what will happen? If it goes through alpha decay, it will be 42. Here will become 48. Here will become 23. Then after that, yeah, this is most likely it lah. After that, if it goes through a beta decay, it will be an electron 0, -1, which will cause it to go from 48 to 48 nucleon number and 24 proton number, which is exactly decreased by 1 here, right? Because this bottom here is the proton number. So A is the definite answer here. Moving on to the final part for this one here for the February-March 2017. A radioactive source is placed 20 mm from a radiation detector as shown in figure 11.1. The initial count rate records by the detector is 150. So it starts off with 150 lah, right? A sheet of paper is placed to the source and the count rate recorded drops to 60. When I put a piece of paper here, it drops to 60 counts per minute from the detector. With the paper still in place, a magnetic field is set up perpendicularly. So it could be either going into the screen or out of the screen lah, right? And when I set it perpendicularly to the direction of radiation, the count rate recorded falls to 20, right? From 60 yet again it falls to 20. And after that they say that the count rate has not been corrected for background. The background radiation is somewhere around 20 counts per minute. So from here they say state the evidence that each type of radiation is present or absent from the radiation emitted by the source. Obviously from here you can see that initially it starts off with 150 ma. When I put a piece of paper it drops to 60. This paper is essentially blocking the alpha radiation, right? Because only paper, anything like even paper can block alpha ma, right? So obviously this is that. Then after that, when I put magnetic field here, it drops from 60 to 20. So this is a clear evidence to show that beta particles is present lah. And since the background radiation is only 20, I know for a fact that there's no gamma radiation because this thing here already reads 20 already, right, after the magnetic field. And because of that, then I know that there's no gamma radiation now. So from here, how am I going to put this in words? Obviously, first and foremost, I'm going to say that alpha particles are present. This can be proven when the paper absorbs the alpha radiation and drops the count from the detector from 150 to 60, somewhere around there lah. Right. Then after that, beta particles are definitely present as well. Why? This can be proven when the radiation count drops from 60 to 20 as the magnetic field deviates the beta particles, right? And finally, the gamma rays are definitely not present. Why? Because background is already 20 lah. Background radiation is 20 counts per second, right? So nothing, there's definitely no gamma radiation. And this is how you're going to get your 5 marks, guys. Everything here. For those who are too slow, please pause the video and copy it down later. Okay, then after that, from here, determine how much original count rate of 150 counts per second, if any, is due to each and every one of the radiation. From 150 drop to 60, obviously this is going to be 90 lah. From 60 drop to 20, obviously this is going to be 40, and this is naturally going to be 0. This is essentially free 2 marks, guys. You just need to know what's going on. Then you can more or less explain your way through the whole thing. Okay? Then moving on to the next part. Right. I don't think I need the video here anymore. Okay. Moving on to the next part here, the notation for isotope sodium is blah blah blah, which rule gives the composition of a neutral atom of an isotope. Number of protons is definitely going to be 11, right? Then number of neutrons could be different. This right now, because it wants an isotope, right now the neutron number is going to be 12 here, right? So here it could be 12. Oh, sorry. Yeah, this is just A, bro. This is not an isotope. This is not even just an isotope. It's just talking about this sodium itself. My bad. Yeah, it's just gonna follow. It's just gonna follow this one here, and you're gonna explain the composition of this sodium atom, right? And moving on, the radioactive isotope of hydrogen undergoes beta decay to blah blah blah. What is the nuclear notation for this hydrogen isotope? So if I work it backwards, this thing was a product of beta decay, which was 0, -1, meaning to say from here it started off with 3, 1. Yeah, it started off with 1 here and 3, right? 3, 1 here. So C is definitely the answer here, right? It's gonna be helium. Hydrogen. When measuring the emission from a radioactive rock, brought into the laboratory, a teacher mentions that the background radiation must be taken into account. What is background radiation? Infrared radiation from warm objects? Definitely not. Infrared radiation from the sun? Nope. Ionizing radiation from radioactive rocks brought into the laboratory? Possible. Ionizing radiation in the laboratory when the radioactive rock is not present? Definitely here, guys. Even though there is no active radioactive samples here, right, there will still be background radiation, because background radiation is always random and present. These are the two conditions for background radiation, right? And finally, for the ABC part, solid cesium-137 decays by emission of beta particles to form barium-137, which emits gamma rays. The barium-137 undergoes no further decay. The half-life of cesium-137 is 33 years. This is the half-life. A block of pure cesium-137 has a mass of 2 micrograms. The diagram shows a radiation detector a distance of 5 meters from the block. The detector registers 2,000 counts per second. Which statement is not true? After 33 years, the mass of the block is going to be 1 microgram. This is definitely not true. Why? Because half-life does not cause the mass to decrease. It only causes the radiation count to decrease. Right? So this is definitely not true. After 66 years, the sample contains 1.5 micrograms of barium. Yeah, possible. It decayed from cesium to barium. With 5 cm lead between the block and the detector, the count rate is just above the count. Yes, definitely, because the lead blocks everything. With 2 mm of aluminium between the block, the count rate reduced significantly. Yes, because it will block. It is actually going to block all the other radiation as well. Okay, so A is the definite answer here. To ensure the safety of workers in laboratories when radioactive sources are used, describe how radioactive materials should be stored. It is definitely stored in lead containers for sure. Lead containers. Lead. Why do we choose lead? Is because lead is the only thing that can stop even gamma radiation. How should it be handled? With tongs and not your hands. Right. It could be anything, guys. Anything that's logical is acceptable. Wearing gloves, using tongs, wearing lead suits, remote control device, anything under the sun that is logical is definitely acceptable. Right. Then complete the table below for 3 types of emission from radioactive sources. Electromagnetic radiation is definitely gamma. Helium nucleus is definitely alpha. Electron is definitely beta. The range in air is always going to be km, m, then cm. Oh, in this case here, it will be cm and m, right? Because alpha is the shortest range, followed by beta, then gamma. So it's km, meters, then cm, right? Absorbed by, obviously, thick lead, right? take lead here, then this one is absorbed by aluminium. Even thin aluminium is acceptable. Just write aluminium is acceptable. Aluminium sheets or whatever. Okay. State the type of radiation emitted when an amarilla decays into this thing here. There's obviously a difference of 4 and 2 here, right? So it's obviously alpha decay. A phosphorus nucleus decays from this into this. You can see that there's a clear +1 here, which is naturally a beta decay. You should know this by now. If not, you're in trouble. Okay, then after that, the next exercise here. What are the isotopes of an element? Definition of isotopes is same proton, different neutron, but with the same chemical properties. So different element, wrong, different element, wrong. Same element with different number of neutrons possible, same number, no, it should be the same proton, different neutron. So C is the definite answer here. The radioactive isotope of carbon-14 decays by beta emission to form isotope of nitrogen-14 and a beta particle. The equation of the nucleus is blah, blah, blah. Right, so Y is definitely -1. This is definitely 6, because 6 minus -1 is going to be 7, right? So obviously A is the answer here. Nothing to explain there. A beta particle is a fast-moving electron. Which statement explains how beta particles are emitted from an atom? An electron is emitted as a beta particle from an inner electron shell. No, if you learn chemistry, it will, if anything, they will donate the outer electron shell. An electron is emitted as a beta particle from the outer electron shell, but beta doesn't work that way. A neutron changes into a proton and a beta particle is emitted from the nucleus. This is the answer. For those who are unsure why this is the case, we can just use this equation as an example. Initially, the carbon is 6 proton and 8 neutrons, right? When it goes through a beta decay, look what happens here. It becomes 7 protons and 7 neutrons. So what essentially happened was one of this neutron is converted into a proton, guys. So this you'll see this more often in your A levels as well, but for now this is that. For those who are ever unsure in the exam, write down the composition of what's going on in a beta particle, in a beta decay. If they don't give you this equation, form an equation of your own and you'll see it much clearer, guys. So C is the definite answer here. Okay. One isotope of iridium-194 is represented by blah blah blah. The isotope decays by beta particles. They want me to complete the equation here, which is obviously 78 and 194 lah. You should know this by now, right? The half-life of blah blah is this amount. So this is the half-life. The sample has an initial count of this amount. Calculate the count from the sample after 38 hours. So it goes through 2 half-life lah, right? So 1100 after the first half-life becomes 550. After the second half-life, it becomes 275, right? So, yeah, nothing much to explain here. 1 half-life, 2 half-life, right? Because it went through 2 half-lives here. So it's going to be 275. Follow the units. If they write counts per minute, you write back counts per minute. If they write counts per second, you write counts per second. But follow the units. It's never going to be just counts per second, guys. Make sure you read the question. State 2 ways which gamma emission differs from beta emission. Gamma is an electromagnetic wave. Beta emission is an electron. Gamma, there is no charges. Beta is negatively charged. Anything along the lines. There's so much, man. Gamma travels at the speed of light. Beta does not. Right? Is anything lah? There's damn a lot of answers that you can write. Anything that's logical is acceptable. Gamma emission is an electromagnetic wave. Beta is not. Then gamma emission has low ionizing power. Beta has higher ionizing power, or gamma have no charges, beta have charges. Anything along the lines anything that's acceptable is definitely logical. Okay, then moving on to the next part here. How many questions do we have more? 8 more pages. Okay. The diagram shows different particles moving through a magnetic field. Which particle experiences a magnetic force acting out of the paper? So it's out of the paper, it's coming out of the screen now, right? So this is the magnetic field. It's magnetic field here, then proton, nope, doesn't work that way. Magnetic field here, proton, nope, doesn't work that way. A and B is a definite no, right? So C here, magnetic field, proton downwards. C will be out of the page. If you do it, guys, from a side profile, it looks something like this, right? The magnetic field is towards the right, the current is towards downwards, and you'll have a force coming out from the screen, so it's like coming out here. And C is the definite answer, right? Then moving on, when Rutherford bombarded tin gold foil with alpha particles, he found that alpha particles were deflected through large angles. Which statement is true? This one is definitely because the mass and the charges are all in the nucleus. Most of the atoms consist of empty space. This is correct. This is a correct statement, but it does not explain this deflection. All of the positive charges and most of the mass of the gold atom are concentrated in the small volume. Okay, good. Positive charges in the gold atom is spread evenly. No. All the negative charges is definitely no. Right. The diagram shows the path followed by alpha particles as they pass between two charged plates. They are deflected downwards. Okay, alpha particles will be attracted to the negative, beta particles is definitely going to be attracted to the positive. What happens to the beta particles passing through the same electric field? They will be deflected downwards. No. They're deflected upwards. Definitely. They are not deflected. No. They are deflected. Yeah. No. Make sure you get this right. If you got this wrong, bad news, guys. The diagram shows the count rate from a radioactive source over a period of time. What is the half-life of the source? From 2000 to 1000, how long did it take? Exactly 1 hour. So it can be no other than B, right? And finally, the last page of this exercise for 2020. The isotope hydrogen-1 has a proton number of 1 and a nucleon number of 1. So this hydrogen has 1 proton number and 1 nucleon number. So there's no neutrons. 2 isotopes of helium are helium-3 and 4. Helium-3 has a proton number of 2. He has a proton number of 2 and a nucleon number of 3. So there's 1 neutron here. Helium-4 has nucleon number of 4. So helium has nucleon number of 4, and obviously I will assume that the proton is still 2. Right. So look at this here. What do you want? Helium. Neutrons. There's going to be 1. And helium, the neutrons, this one is obviously going to be 2. Number of electrons will be the same as your proton number. So it's going to be 2, 2 here. Because this is 2 and this is 2, right? And the mass compared to the neutral atom 1 is going to be comparing this and this versus this and this. This. So it's obviously going to be 3 and 4 because the nucleon number is the atomic mass number as well, right? So yeah, 3 and 4 definitely. Right. Then moving on, an experiment takes place in the laboratory. Shield from all background radiation. A sample of radioactive material is wrapped in aluminum foil of 0.1 mm. A detector of ionizing radiation placed 1 cm from the foil records a reading. A piece of aluminum of thickness 5 mm is placed between the detector and the foil. The detector reading drops to 0. State and explain any type of radiation passing through the aluminum foil. Okay, so there's 2 situations here, right? Right now, the first situation is I wrap it with 0.1 mm of aluminum foil. The detector still records a reading. Then after that, I put aluminum of thickness 5 mm between the detector and the foil, and the detector drops to 0 straight away. There's no background radiation. Now, it's either going to be there is alpha, beta, or gamma only. Let's look at alpha first. Today I know for a fact that there's not going to be any alpha particles here, because even though this is only 0.1 mm, a piece of paper is sufficient enough to block the alpha particles already, right? So if it was really alpha particles, then the reading should have dropped, not still record a reading. I know there's no alpha particles. I know for a fact that there's definitely beta particles lah. Why? Because when I put 5 mm of aluminium, the reading drops straight away to 0. And I know there's no gamma particles, because if even with 5 mm of aluminium, the gamma particles would have penetrated straight through. So I know for a fact that alpha and gamma is not present, only beta is. So how am I going to state and explain? It's going to be something along the lines. Alpha particles are radiation. Alpha radiation is not present as the 0.1 mm of foil would have be sufficient to absorb the alpha particles, causing the reading to drop significantly. Beta particles are present. This when the 5 mm is placed, 5 mm aluminium is placed between the detector, the reading drops to 0. And finally, gamma radiation is not present as 5 mm of aluminium would not have blocked would not have dropped the reading. Something along these lines. Right. Okay. And moving on to the next part, yet again, the same question. So there's beta particles here flying through flying through the magnetic field. I know for a fact that if beta particles is going towards the right, the current will be going towards the left. And from here, I'm supposed to use the Fleming's left-hand rule yet again. Magnetic field pointing into the page, then my current finger pointing towards the left, and finally a downwards force here. Obviously, it's going to go downwards here, down to the page. And thus, C is the definite answer here. Okay? Then the arrangement shown is used to check whether the flour inside a cardboard packet is above a certain level. If it is above this level, the flour absorbs the radiation from the source so that it doesn't reach the detector. And this is quite a famous IGCSE question, guys. You need to know what's going on here. This setup, right, is essentially how the Coca-Cola cans and all the things that require filling knows when to stop. So essentially, what's going to happen is there's going to be a radioactive source here that is continuously beaming and being detected by this detector here, right? As the flask slowly fills up the can, the detector, once it fills up to this specific spot here, right, this flask is actually going to block the radiation source, and the detector drops a significant amount of count rate. The significant drop is actually going to trigger the input, which stops pumping in more flour into the packet. So this is essentially how the whole thing works. It could be in flour, it could be water, it could be something, but it is a very famous usage, right? So which type of radiation is suitable for this? It's definitely not going to be alpha, because if it is alpha, this cardboard would have blocked everything from the detector. These kind of situations we usually use beta, because it is just in between the right amount. It's not going to be gamma for sure, because it will just penetrate through everything. It's not going to be stopped by anything at all. If you see these kind of questions in your exam, make sure you circle beta as the proper radiation, because it's just right. When there is no flour, it will go through. When there is flour, it will be stopped here already, which causes a drop here, which causes the input to stop pumping in flour already. This is how it essentially works. Very important, guys. You need to know this. Okay, then a nucleus of americium blah 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 emits alpha particles to form blah blah blah. What's the equation? Alpha particles fall to, this is wrong already. This one becomes plus. Obviously donkey is the answer. You should know this, nothing to explain. A certain element has several isotopes. Which statement about these isotopes is correct? They must have different number of electrons. Nope. They must have same number of neutrons. Nope. Same proton, different neutron. Always remember isotopes, same proton, different neutron. Same number of nucleons? Definitely not. They might have the same number of protons. Definitely donkey here. Okay. A reading is taken every 10 minutes of the number of emission per second from a radioactive source. The table shows the reading from 800 drops to 400 in 20 minutes. What's the half-life? 20 minutes. Nothing to explain. Okay, a very important experiment increases scientific understanding of the structure of matter. In this experiment, particles scattered as they pass through a thin metal foil. Oh, the gold foil experiment. Which particles were used and to which conclusion did the experiment? Definitely alpha particles, not this, not this. Matter is made of atoms. Atoms have very, very small nucleus. Definitely be here, right? Below are the symbols for 5 different nuclei. Okay, 1, 2, isotope, and no more. Which two are the same element? Same proton, different neutrons, right? So obviously A is the answer here. A radioactive decay can be presented as shown. The equation is incomplete. This decay must be a definitely beta emission, right? Because if you plus the 0, -1 here, it'll be 91 minus 1, which will give you 92, right? The graph shows how the decay rate of a radioactive source changes with time. 4000 to 2000 is here. What will be the decay rate after 8 days? So the half-life is 2, right? 8 days is 4 half-life. 4000, first half-life to 2000, second half-life to 1000, third half-life to 500, and the final half-life, which is the fourth half-life, to 250. So obviously the answer here can be no other than C, right? You just need to know how long it took only. Below are 4 statements about isotopes of a certain element. Which statement about the isotope must be correct? They are radioactive? No. They are unstable? Maybe, but not must. They have same number of neutrons? Definitely not. They have same number of protons. For sure, this is the very definition of an isotope. Right. And from here, which diagram represents the experiment that proves that evidence of a nuclear atom? Definitely not beta particles, right? Nuclear atom, obviously this one lah, right? Why will the gold nucleus attract the alpha particle? If anything, it's going to deflect it away because the nucleus contains positive charges. Sodium 24 decays to magnesium 24 according to the following equation. Emitted particle, only explain so much, is beta. This one is one of my favorite questions, which I have probably gave you guys in class before. A reading on the detector placed near is this amount. The background is this amount. The half-life is this amount, and the reading. What is the reading on the detector after 68 hours, which is 2 half-lives, right? So initially it started off with 536, but this is inclusive of background. So you need to minus this off, minus 44 here. You'll get 400 and 92. Is it? Yeah, 492. Yeah. Then from here, this is the thing that decays. First half-life will become 246. The second half-life will become 1, 2, 3. But this is not the final count because they want the reading from the detector. Reading from the detector is inclusive of the background radiation. So if you found 1, 2, 3, you're supposed to add it up as well. And at the end of the day, you're supposed to get donkey as your answer because 1, 2, 3 plus 44 is going to be 167. And finally, to the last 2 questions here. Bismuth is radioactive. It has a half-life of 20 minutes. The nuclei notation of bismuth is blah blah blah. State the composition of the nucleus. The nucleus only contains protons and neutrons. So my proton number is obviously going to be 833, and my neutron number is everything else, right? Which is 214 minus 83, giving you 131. Just write proton number 83 and neutron number 131. You would have gotten your full answer here. Bismuth 214 decays by beta. Beta is 0, -1, so it's 214 and 84 here. Nothing much to explain. The count rate from a sample is 360 count predict the count rate after 60 minutes. The half-life was 20, right? So there's 3 half-lives here lah. Is there any background radiation? No. So I just decay this straight away. 360, 1 half-life, 180. Second half-life becomes 90. The third half-life becomes 45. So that's why it's 45. What's the radiation? Counts per second, guys. It's supposed to be counts per second. And state 2 of the social or economical environmental issues involved in storage of radioactive materials with very long half-life. Social means to say what people are unhappy about. Economic means to say how it affects them in terms of money, and environmental is basically affecting them in terms of the pollution or whatnot lah, right? Social wise, people are definitely going to be unhappy. Why? Because it's basically going to be a long-term problem, right? After a while, then it's going to cause sickness, and it's going to cause people to move away, because the radiation count is too high lah. Economical wise, it's definitely going to cost more because storing radioactive materials requires a lot of money. And the environmental wise is definitely going to cause pollution over a long time on a piece of land. But if you write just down two of any, this is definitely acceptable, right? So 2 of the social, economical, environmental issues involved with very long half-lives. Oh, am I supposed to write? Yeah. So social-wise, it will be this according to Mark's schema, right? Fear of cancer or sickness in people. Economical-wise, it will be a high cost of storage and also reduction in tourism, which is essentially money. And environmental wise is obviously going to cause pollution lah, right? Causes pollution to the lands and possibility of contamination of water supply. Anything along the lines. You can just pick either 2 and you'll get your free 2 marks. Ooh, almost there. Then finally here, radon-222 is 220 is a radioactive material. The nuclear notation of radon is this. Describe the composition of a neutral atom. If they're asking about a neutral atom, you're basically supposed to talk about the proton, neutrons, and electrons. Which in this case here, obviously the proton and the electrons are going to be 86. Write it in Word, guys. Don't write this here. Right. And the neutrons are basically 220 minus 86, which is essentially 134. Write it down in words and you'll get free 3 marks. Easy. Right. A nucleus of radon-220 decays by blah 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 again. It's alpha decay already. So it's 216 and 84 here. Easy. Free 3 marks. It's free. It's free real estate. Okay, a detector of radiation is placed near a sample of radon-222 and gives a reading of 720 counts per second. The half-life is 55 seconds. Calculate the reading after this amount, which is for half-life. Ignore background radiation. Good, easy. 720, first half-life becomes 360, second half-life becomes 180, next half-life becomes 90. And the fourth half-life becomes 45. So easy, 45 counts per second. Follow the units yet again. State the values of x and y, proton, neutron. So y is definitely 91, right? Nucleon number is 143 minus plus 30, 91, which is going to essentially give you much 234, 234, right? Easy. And beta decay. This is PA, right? So it's 234, 91. And goes through beta decay. It's 234 and 92 here. Easy. Another 2 marks. Radiation detector measures a background count in laboratory of 30 counts. Suggest 2 naturally occurring sources of background radiation. Guys, I've mentioned this a lot of times in class. You need to know where the sources are coming from. My personal favorite is cosmic ray or building materials. But the 4 are going to be soil or rocks building material cosmic ray. Alright, so if you write I need two of it, it's definitely acceptable, but my favorite is cosmic ray, so I'll write cosmic ray and building materials. Anything along the lines is acceptable, right? And finally, the sample is placed in the laboratory close to the count rate is 544. This isotope has a half-life of 400 minutes. Predict a value for this amount. Guys, a lot of students, after they see this question, right, they totally forget that the background is this. Guys, these are all connected together. So be very careful when you're doing this calculation here. Yet again, 544 is inclusive of background. So you actually need to minus the 32, which is going to give you 512. 512 is the one that goes through half-life decay, which will give you 256 and then 128. How many? Oh, 3 only. So this is 1, this is 2, and this is the third one, 64. But this is not the final answer because they want you to predict the count rate at the detector later on, right? So you need to add back the background radiation, which is 64 plus 32. At the end of the day, you're going to get 96. And what's the count? Counts per minute. This one here, it's supposed to be 96 counts per minute. So just one reason why the count rate measured 120 minutes later may differ slightly from the value predicted in here. I've said this many times, all this calculation is best case scenario. In reality, there will never be an answer that is calculatable, right? It's all assumptions, right? So the prediction here is, this is the prediction, but in reality, you know that background radiation is supposed to fluctuate up and down and randomly fluctuating up and down. So if I were to state, it's because background radiation is fluctuating randomly, right? This is your reason, and this concludes the final exercise.